record.
Okay.
And hand it over to Thibaut.
Yeah, I'm gonna share the my screen. Let me know if you see the right thing.
That looks good.
Okay, awesome. Yeah, I'm on a dual screen setup, so I just want to make sure that you're seeing the right one. Awesome. So let's start then. Hop. So thank you everyone for being here today for this presentation of my research that I did for my PhD at UBC, and with the title for the thesis, A Framework for Joint Petrophysically and Geologically Guided Geophysical Inversion. So this research was done under the supervision of Douglas Oldenburg, with the GIP group, and we implemented within the SimPEG package in Python. So my objective today is to present you the work that I did for to tie together geophysical, petrophysical, and geological information in a single conventional inversion framework. And by petrophysical here, I mean physical property information about the different rock units. So the overview for this presentation is gonna mostly follow the structures of the thesis and publication. So I'm gonna start by an overview of the state and the motivation, and then lay out the foundation of the framework I've developed, which was published in August 2019. And then we're gonna move on to the generalization of that framework to multiphysics inversion. And we're gonna finish then with a case study utilizing this framework on a kimberlite pipe in the northwestern territories in Canada. And this case study was published just recently this summer too. So this example, actually case study, we're gonna use it as a motivation throughout this presentation, both with in synthetic and the real data case. So to present you like an overview of that motivation example. So this is the geological model from borehole of the DO27 kimberlite pipe in the Northwest Territories in Canada. So this kimberlite pipe is diamantiferous, and so the way it's composed. So we have it's embedded in a granitic background and overlaid by some till. And so we have the main diamantiferous unit here, the PK unit, which has a very, very low density compared to the background. And also, so PK stands for pyroclastic kimberlite. And here we have a volcanoclastic kimberlite, we name VK, which has also kind of the same characteristics. And then we have a unit that's strongly magnetic, hypabyssal kimberlite. So in the synthetic, we're just gonna consider like an induced field, but in reality, and in the case study, it's actually remanent, meaning that it's not only a magnetic field induced by the Earth's magnetic field, but it has its own proper its own field. So the geophysical problem in a nutshell. So geophysics, its goal is to probe the subsurface to image geological structures and based on physical property contrast in the background. So for example, here if we have like our pipe and we have like units with low densities or high magnetic, we can, for example, measure the variation in the gravity field or variation in the magnetic field of the Earth. And if we take data at the surface, we end up with that type of data maps at the surface. And so with a low in the gravity field and a high in the magnetic field. And the goal of geophysical inversion is from those data we acquired on the field to go from the data to an image of the subsurface. So for that, what we do is we discretize the Earth. So by that we mean we divide it into different cells, or like kind of a pixel in an image, and we want to populate it with physical properties values that's gonna give us like an image of our subsurface structures. So the way we do that to go from the data to an image is through the minimization of an objective function, and with M being basically the physical property of each cell here. So that's our variable. And this objective function has two parts. One is the data misfit. So we want that the physical property distribution we recover in the image reproduce the data we have. So that's what this measures. But it's also a highly non-unique problem. Like we might have here in this example, 1,000 data points in each data set, while we might have like close to 1 million pixels in the image. So for that, we need a regularization term, which basically adds prior information to the problem so we can solve it. And one of the most common inversions that is done is a least square or Tikhonov inversion. And so it's characterized by regularization in terms of a least square difference between a reference model and our current model. And it usually has two parts. It has a smallness, which measures the distance between our recovered model and some reference model that we design, for example, from geological modeling, or just a half space, so like a constant model if we don't have any more information. And we also have a smoothness term, meaning that we want the variation in space to be gradual and fairly smooth then. And for example, with that type of inversion, this is what we would recover from the gravity and magnetic data we have. So as we see here, we recover a density model for gravity and a magnetic susceptibility model for the magnetic data. It's all synthetic at the moment. And we see that it's well centered on each of the units that's causing the anomaly. So on the pk unit here for the gravity and the hk unit for the magnetic. But as we see also, like it's a very smooth model. There is no like sharp contrast to be seen. And also there is no way at the moment to link the gravity and magnetic data in that type of inversion. So if we want to go back to some sort of a geology model after that, we can do a post inversion classification. So here I'm plotting, for example, the scatter plot of the two models. And as we see here, we have like a continuous range of values as we expect from that type of inversion. And I also put on that scatter plot the real physical property signatures of each rock unit as I used in that synthetic. And we can see we're quite far away from reproducing those physical properties for identifying the different rock unit. And if we do any sort of interpretation, as you see with the coloring here, it will be highly dependent of any threshold we choose. And all these behaviors are actually very expected, because in what a least square inversion does in the end is by if we take a smallness that's in the shape of a least square, it actually means that we're assuming a normal distribution of the parameters m. So this we call it, instead of thinking of it as a regularization, we call it a prior distribution, and there is a one-on-one relationship between priors and regularizers. And so here I plot on these figures the Gaussian distribution assumed for each of the inversion. So that's kind of summarized kind of the state of the field as it is for inversion and how it's commonly done. And there is two problems I can see with that, is that so we don't reproduce the petrophysical characteristic of the rocks, even if they are known. We don't reproduce them in the inversion. And because of that, and because we get that very continuous distribution of physical property parameters, it's very hard to do some rock identification. So my goal today is to kind of address those two problems, and by including additional information in the inversion. So that I want to recover from inversion to recover a result that is more geologic. And so for that, I have two progress to make. Is that I need to have each pixel or each cell of my model to reproduce physical property signatures that's associated with a known rock unit, and with that use it as a geological identifier to create a geology model from the inversion directly. So that's the start and motivation for the framework I've developed for linking geophysics, petrophysics, and geology. So this framework was published last year in JGI, and it came with an associated GitHub repositories for reproducing all the examples that are in that papers. So to include physical properties, we first need to model it, and like one very common, so as we already seen, like one very common probability distribution is the Gaussian distribution. And what we can do is try to characterize each rock unit and its physical properties by a Gaussian distribution. So for example, here we can have the background and we can characterize its density and magnetic susceptibility with Gaussians in a two-dimensional space, and we can do the same for the pK unit and the HK unit. So like if we have samples for each rock unit, we can compute the mean and covariance of that Gaussian distribution quite easily. And the way I can put that all together is actually very simple, is by weighted summation of this different Gaussian distribution. So that's what we call a Gaussian mixture model. So it's just a sum of the different Gaussian, and that's going to be my representation for the physical property information of the model. So for example, here for the TKC example, that's what I will get with a background unit, an HK unit, and a VK unit. So each Gaussian distribution is centered on the mean physical properties of each unit, and with some variation around that mean. So it's quite a complex problem now, because like I have geophysical data that I want to invert. I also have petrophysical data I want to include, and I might also have some geological data, like for example from borehole, or like relationship between units, etc. And I want to link all of those together, and to be able also to formulate assumptions on the number of units or the physical properties if they are not known, etc. So what I do is each of those diamonds, here's the inversion, characterization, and identification, I turn them into an inverse problem, and that are linked together. And it's a lot, and I'm going to present each step of them just in the next slide. But it's a lot of moving pieces, and now that we have multiple data sets, we also need to reach a target misfit for all of them at the same time to ensure that we fit all of them. So to link all that information together, I'm actually gonna change the smallness regularization, or more precisely, I'm gonna replace the Gaussian priors for the smallness in the inverse problem by GMM, so Gaussian mixture model priors. So how I design these priors now for this new inverse problem is this way. So it's a GMM models, but it includes different type of information. So here I have the product just to say that it's all over the whole mesh with n the number of cells. This summation here is the number of expected units. So here in that case, that would be 3. Here's the proportion in front of each unit is actually at each cell, how much do I expect each unit to appear. So that's where you can include, for example, geology information about if you expect a unit to appear more at one place than another's. And then we have the Gaussian distribution. And so what it does here, so we have our mean, which has a mean of the physical properties of each unit. So that's going to play the role of our reference model. And then we have the covariance of each unit, so to have information about how tight we want distribution, or if there is correlation between physical properties within a same rock unit. And I also include here like the typical weights that we use in geophysical inversion. So like usually, for example, depth or sensitivity weighting. So this is quite a complex priors, but I'm gonna use now like an approximation that's more detailed in the thesis. But basically, if the units are distinct enough, like kind of in that case, so if there is not too much overlaps between units, I can still approximate that priors with a least square inversion. So that means I can rely on like compiled codes that have been written and on all the literatures. And so I'm going to show you how, what are the different steps for the inversion now. So taking that framework, that the pictures that I've showed you before, looking at the geophysical inversion inverse problem. So it actually doesn't change at all from before. I have some input geophysical data, and I have some prior information in terms of reference model and the smallness weight. And then we take a step of minimizing the objective function with that prior information. And here I'm just solving it as a nonlinear problem. So I'm just taking one step of the inverse problem, and I get a new model M from that geophysical inversion step. The next step is petrophysical characterization. I'm going to show you an application example soon, but basically what I want to do here is to be able to include prior information. For example, if you have physical property measurement from a lab, etc. So that's my prior information I have. But I also want to be able to include information from the geophysical inversion into characterizing the petrophysical characteristic. So I want to be able to learn a petrophysical distribution from both what I know from the lab, but also from the geophysical data itself. So that's done through what I call the MAPM algorithm. So what it does here basically is that if I have my geophysical model M here that has this distribution with the histogram in blue, and my prior distribution of physical properties here is a gray line and dashed from, for example, from labs or ball measurement. What the MAPM algorithm is going to do is basically an average of the two distribution. And you can weight the average to like rely more on the physical properties from the lab or more on the geophysical inversion. And then we update that new GMM to give us new parameters for the petrophysical distribution. And then the geophysical step is basically for each cell to identify to which unit it belongs to based on its physical property and the current GMM distribution. And from that, we can update from this assignment, we can update the reference model and the smallness weight at each cell. And then we start over the process with the geophysical inversion with the new updated values. So to show it in a bit in action, here I show a very simple problem. So with here I show the Tikhonov inversion. So like the black line is the true model, the blue dashed line is the reference model, and the red is the geophysical model at each iteration. So you see in the Tikhonov inversion, we usually have like the reference model that stays at the same place, and we stop when we feed the data themselves. In my PGI inversion, we see that the reference model is updated at each iteration. And we stop when we fit both the petrophysical and the geological data. So I've designed target misfit for both Phi-D and for my smallness. And they follow kind of the same pattern because they're both least square term. And so I talked about before, like about now, about why that I want to learn the petrophysical distribution, and why I want to do that is because I want to be able to work with partial, incomplete, or even like no petrophysical information. So here I show you an example with a DC example. So that's here my true model with two cylinders, one conductive and one resistive. And here I show you what you get with a Tikhonov type of information. Below, I show you the result if I provide the algorithm with the true physical properties values, and I fix them. So like the algorithm knows the true petrophysical distribution. And here in that last slide is where it gets interesting, is that I launched my PGI algorithm, but I didn't provide any type of information to the in terms of physical properties accept that there are 3 units. And I let the algorithm, so the MapEM algorithm, define a new petrophysical distribution at each iteration. And this is what I get. So I do not recover the true mean of the physical properties, but I'm able to recover sharp bodies that have somewhat the right shape. So that is all just from making the assumptions that you can now make with that algorithm that there are 3 units. Find me a model with 3 distinct units, and that's what the algorithm does. So that's summarize the first papers. So that's so we've developed the PGI framework. We formulated as 3 interlocked inverse problem, and which each is fitting criteria, and it provides us tools that we didn't have before about making assumption about either the number of units in the model or the petrophysical signature of the unit. And so far, I've applied it to single physical property problem, but the real power of that approach is that I can now use the physical property and geology information to make a joint inversion. And so that's gonna be the next chapters. So this one was published just this summers, and it also comes with GitHub repositories to reproduce all the examples from the papers. So back to the TKC example. So that's where we left in the introduction with our common least square inversion. So that was our model, and we had the gravity, magnetic, some sort of interpretation with the colors, and the physical property distribution we were recovering from those 2 inversions. So now I can apply what I just developed in the previous chapters, single physics inversion with the framework, so for the gravity and the magnetic. And one thing that happens here is actually, if I consider the gravity and magnetic data alone, I can explain them totally by assuming a single unit. Like for the gravity, for example, I don't need the signature of the HK unit. I can reproduce all the data with only PK. And same for the magnetic. I can only assume I can only assume a HK unit, and it will reproduce the geophysical data. And I'm not going to develop it here, but if you don't provide any other information, adding more units to the information is not going to do any good. It's going to be mostly like doing layers and like halos around inversion. Because there is some sort of a discrepancy principle here that you can try to assume the lowest number of units possible. And now, even so, with that added geophysical property, with that petrophysical properties information added to the inversion, I still have a problem when I combine the model, because I still have a massive volume that has both very low density and a high magnetic susceptibility, and which correspond to no non-rock unit. So I still have a lot of uncertainties in that area, for example, from the inversion. So to counteract that, my solution is to just invert everything together in a single inversion. So the gravity and the magnetic data, and now using the full 2D physical property distribution to invert together and use it as a coupling bit for the gravity and magnetic data. And this is what I get. So this is quite a big improvement now, because so I don't have this overlapping of density contrast and magnetic susceptibility as before. And so you can see in the inversion that I recover fairly well, also, like the location of each PK and HK unit. The physical property distribution are well recovered. And in the geological model, what we can see here is that we have information we didn't have before. Like we have like some information about the dip of HK, which was appearing just as something spherical before. So that's the result using the full petrophysical information. But as I said before, it's like we're unlikely to have it in real life. So what do I do if I don't know the real petrophysical signatures? Well, I can make assumptions about what's happening here. And if we look just back at the least square inversion, we saw that the two magnetic and gravity anomaly are not centered at the same place. So what I can do, for example, with this framework is I can assume that there are 3 units. One is the background. I can assume that one has a low density but no magnetic response, and that another one has a high magnetic response but no density contrast. So it's not true, but it's a good approximation enough, and that we can make just by looking at the least square inversion. And so using that assumption within the PGI algorithm, this is what we will recover. So as you see here, I have one clusters that has mostly only a density contrast, and here I have a cluster that only have a magnetic susceptibility contrast. And this is the gravity and magnetic model I get in the geological model. And as you see here, even though it continues quite at depth here for the magnetic because we underestimated it, there is still information about the dip of the inversion, about the dip of the HK unit, which we didn't have with any of the single physics inversion, even with petrophysical information. And here I show you how the mean of each unit varies in time. So for example, here that's the mean of the clusters that we can identify as PK. So like we are learning a new mean at each iteration. And while we keep the background and the HK density contrast at 0, and reverse for the magnetic susceptibility, where HK is moving and we keep the two others to 0. So that's the end of the methodology papers for the multiphysics inversion. So we generalized the PGI framework to to multiphysics inversion. They are linked through a single smallness term that include all the petrophysical information, and we also generalize the learning of the GMM parameters to still be able to learn a proper petrophysical characterization with joint inversion. And so now I'm going to move to the real case study of TKC, and that was published just this summer in the interpretation. So to present you with a real data set that I worked with at TKC, there's still like a magnetic data sets, but as you see here, like it's not well centered on HK, and there is a negative magnetic here, and it was identified in previous papers that there is a remanence. So now we're gonna work with magnetic vector inversion, so meaning we're not gonna invert only for amplitudes, but for the full magnetic vectors, because now the HK unit, we have to recover its own orientation too. This is a gravity data, very similar to what we got in the synthetic, except for that Norton extension here that is not explained by the pipe. And we're gonna see how that affects our approach here. And we also have like a airborne gravity gradiometry data set that we also include. So now I have like three geological surveys that I'm inverting all together. So for the physical properties information at the site, for the density, I took this cross-section from a report from the drill hole campaigns that shows there is a strong correlation between depth and density contrast, and it's almost linear the way they represented it. So how I include that information in the inversion is actually by including the elevation as a fixed parameter in the inversion and in my GMM. So that's gonna be, so here I present you the 2D GMM that's gonna be for my density. So here you see that I have density, so it doesn't like, and here on the y-axis, the elevation. So you see the elevation doesn't affect at all what I identify as background, but here I have a linear trend for density. And from the petrophysical measurement we have, we actually assumed that HK had no significant density contrast. It came up at about the same as the background. And doing the single physics PGI for the gravity. So here we're inverting gravity and gravity gradiometry together with that linear trend at depth as we saw. And this is the result we got. So we see the outline of the pipe is well recovered, but we have this massive extension here in the northern area. So we know from the drilling that, as you see here, there are some near surface kimberlite, but they seem to appear only as a smooth features here, and that's still classified as background. And we're gonna come back to that a bit later. In terms of magnetic representation, we only had 4 samples for the amplitude of HK, but we measured both the magnetic susceptibility and the Königsberger ratio, which measure the strength of the remnant field. And what we see here is that the remnant field is 10 times stronger than the induced field. So this is the dominant field really here at TKC. And from previous studies, that's from De Vries and al., they estimated from the magnetic data the orientation of that remnants. So using this information for amplitude and this information for orientation, we designed this 3D GMM for the three for the 3 parameters of the magnetic vectors in Cartesian space for simplicity. So like here we represent the amplitudes in X, Y, and Z of the magnetic vectors. And inputting the magnetic data with that information, this is a magnetic vector model that we recover. So we see that we recover fairly well the distribution. So that's the background here. And the orientation defined by De Vries studies is well recovered. When we're well centered around the main body part of the HK bodies, except that we are missing this eastern extension. But same as in the synthetic, when I combine them together, I have like I have a big area that has both gravity and magnetic response, which doesn't correspond to anything we know about the petrophysics in the area. So next step, obviously, is to move to the multiphysics PGI, and that's what we get with the same kind of outcome as before. So we remove that uncertain zone with the wrong petrophysical signatures, and magnetic vectors are still kind of well recovered. And you see here, for example, in the magnetic inversion, that the orientation of the magnetic field for PK and HK are different, because PK is mostly induced field, so it's oriented as the Earth's magnetic field, and for HK we orient it based on its remnant formation, and we're able to have those different orientation within the same inversion. But the problem here we have is more geologic, actually. As I mentioned before, we have this massive Northern extension of the PK unit in the north, which has not been seen in boreholes, and that's an issue. And we see here that we have near surface kimberlite that we do not recover. And so the assumption we can make now is that actually like the contrast in the pipe of density is quite strong. Like we're almost at -1 gram per cubic centimeter. It's massive. And it's very possible that outside of the pipe, those near surface kimberlite have a different gravity response and different density. So now we can, with that framework, we can make the assumption about a force unit, and we can make assumptions about its petrophysical characteristics. And what we did here is actually we run the PGI inversion with many different parameters for that force unit. So here I show you the new, here for example, a new GMM distribution. So you see here we still have the background and PK unit with the linear trend, but here now we add another unit for the near surface. So we limit it in terms of elevation to quite high, and we tested it for various mean and covariance. And we choose basically as expert knowledge, with expert knowledge, what we thought will be the best in the area. And that's then then we include that information in the final multiphysics inversion with 4 units. And that's the final result. So we got rid of that Northern extension and route it back to the near surface with a different density signatures, and that matched quite well what we saw in the borehole. We still have the same properties for the magnetic inversion with different orientation for the different units. The HK unit is not as well clustered as before, but what we gain here is that there is actually much more fits between the orientation of the unit and that we cover and the depth observed in the borehole. So we've actually gained some structural information here, even though we're less clustered. Because before in the previous physical property multiphysics inversion, it was appearing just as a flat inversion, like a kind of like a block. And so that's the summary of our case study. So we show that there are many deficient inference we can make from single data set, even though we can include physical property information. And we also showed like how we can use that new PGI framework to include to make assumptions about another unit that has not been mapped or sampled properly. And we're able to fit all the potential field data at the same time, as well as the physical property information, and include information such as also like trend with depth, etc. So, and that concludes our presentation of this new framework. So, as a summary, I consider the inverse problem now as a 3 interconnected estimation of the geophysical model, the petrophysical distribution, and a quasi-geology model. And this framework is quite general. It doesn't depend on the geophysical method you use. We solve everything as a nonlinear problem, and so we can couple any type of geophysical data together. And it adds quite a lot of tools to formulate assumptions that are directly related to the geological problem about the subsurface. And as a last note, I also want to thank all of the SimPEG and open source community that made this work possible. Like, it was quite a great experience that I very enjoyed. So thank you so much. And 36 minutes.
Nicely done, Thibaut. Well, do folks want to chime in with questions?
So like now we're like pretending like as a, I don't know, external examiner and then attack people. Is that
it's as you wish. If you have questions, I'm very happy to answer them. And if you have comments about the presentation itself, it's welcome to it. I don't think it needs to be separated. If you have comments, make comments. If you have questions, ask questions. It's fine.
If Sagi's ready to go on the attack, go for it.
Yeah. Yeah, so Thibaut, I'll try to attack.
Sure.
So the main assumption made in your PGI is a Gaussian assumption of petrophysical distribution.
Yes.
But in reality, like, I mean, it could be, but in reality, it may not be the case. So,
true.
So how your algorithm sort of handle the real distribution?
So, I've not emphasized this here, but it can be done in different ways, and that might work well or not of the problem. So, for example, for electric conductivity, it's the distributions appear Gaussian as a log space, but it's fine because we often invert in the logarithmic space for the inversion too. So in that case, it's quite quite non-problematic. Where I got problems was more for the magnetic susceptibility inversion, because magnetic susceptibility is in reality follows more like a logarithmic distribution too, while we usually invert it as it's a linear problem, and we invert it as we invert it just as a linear properties. And I try to use the mapping in SimPEG to take the linear problem and invert with log probabilities, but it didn't work quite well. I think there is a lot of things to do on that side. And my main problem was that because it's a linear problem, using the log of magnetic susceptibility, my sensitivities then we're having kind of like an exponential range. There was, and because we're doing inversion based on the sensitivity, we're taking a step. Very quickly, the inversion was getting stuck because a small area was having a high sensitivity and the rest was not that sensitive and was kind of locked. So what I did for the real case scenario for the magnetic vectors was I defined and also I didn't have much information. Like I had, as I said, I had 4 samples and then I have an estimation of the orientation based on the Vries and al. Studies. So what I did is I first defined a GMM with the log amplitude and angle space, and then I sampled a lot from that distribution and transformed those samples into Cartesian, and then fitted those Cartesian sample with a GMM distribution. So that's what's kind of my workaround. Like I'm sampling from logarithmic amplitude and angle space, and then coming back to the Cartesian space to get to some sort of like to take some sort of like a middle ground. It's like and so that's why if I go back to the distribution here, like this is my background, and you see this is super small compared to the extension of the HK unit, but at the same time, that's also I got all the correlation, assuming the amplitude and the angle were independent, then the 3 components of the in Cartesian are not, they have like strong correlation as you can see here. So that's kind of my middle ground.
Okay.
Thibaut, do you think because those Gaussian maps are super driven by I guess the width of the distribution, do you think there's a bias towards sending anomalies or sending like basically cells towards like the broadest families or the broadest classes?
I will try to answer. I'm not sure I got your question well, but I'm going to use that slide. For example, like if you see in that inversion, this is my the off-white colors is my background, and here the red is the orange. And you see that here in that inversion, most of my mesh cells are included within that very small Gaussian distribution, and this is the red. So actually here, most of the cells are contained within the smallest Gaussian. Is that what you're asking?
Well, no. Most of the cells are in the largest group, right? Are in the big orange patch right now, which is
here's the orange. Those points are the red cell colored in the inversion, right? And you see that most of the mesh are white.
That's true. Right. Yeah,
it's just that here it's just so small you don't see it. That's the tricky part. Is that I agree that the area of influence of the HK unit is very big when you because we converted from a logarithmic space to a linear space. So what seems okay in log space now in linear, like the small variation for the background HK appears so small, but they still contain 90% of the mesh or more.
Yeah, that's great. Can I ask another one?
Sure.
So we had lots of conversation about this, you and I, right?
Yes.
So my next question is the issue that I always see is that the influence of the Gaussian mixtures is there's no spatial component to it, right? So they kind of expand throughout the entire mesh, right? So what's your next step to be able to be a little bit more spatially oriented in a sense?
Well, we kind of started to do that with that last inversion here. Do you still see my screen? Just to make sure. Yeah. Like what we did actually, like, so we have here we have those two units that have like so we have this pK that's in the pipe unit, and we have this near surface kimberlite. And one thing I didn't want, for example, was that near surface to override the pipe. And so in that Gaussian mixtures, like in front of each Gaussian, there is that proportion, which is my geologic information about what's like before any measurement, how likely each unit is, like what's my expectation of each unit. And so basically here what I did is that we have like from the geologic info, like what I included as geological information is that the pipe, the maximum of the pipe is that noting at 133,680 meters for the noting. So basically here's the likelihood of the pipe unit to appear north of that limit is 0. Like this unit, the pipe unit cannot appear further north. That's what we mapped with the boreholes, and that's why we kind of like cut it here, but it's taken over by this near surface near surface unit. So we can actually vary the properties of the GMM, especially by varying the proportion.
Yeah, that's great. That's great if you know this, right? But in let's say you're in kind of more of a greenfield setting, and then you're not too sure. Can you foresee? I'm not asking like if you have our done it already, but can you foresee like a way that we could automate that kind of picking of or have more like a spatial variations of your groups, basically? Who can turn off groups in one area because of something? I don't know. I don't know if you thought about it.
Yeah, it's like there is possibilities for that. I've not played too much about it because, as I said, like for this MAP-EM algorithm, like here I've shown mostly what I can do by varying the mean, but I've defined similar problem for the covariance and the proportion. And I have an example in the thesis for the covariance for a groundwater problem where we don't know the mean and we don't know too much about the covariance either. So I let both works, but and the proportion I used it less, and because what you just said, I consider it as a danger at some point, but maybe there is some application, is that you can also vary the proportion either globally or locally. The problem that can happen maybe, and like I turn it off in those problems for that, is that like is that some clusters might, like if you vary the proportion, some clusters might turn off at some point. So we're having a proportion of 0, and then they are very hard to reactivate. And so I prefer to present it as make an assumption about the number of units, and I'm gonna recover an inversion with that number of units. But you can also try to maybe vary the proportions locally, but you have the risk of like maybe losing some units. And I've done some work, but it's more like in the development section of the thesis too. I have some picture here where I'm using image segmentation to vary the proportion also locally. And let me find the picture for that. It's not a geological image, but so here, if you see the example, it's I'm just using this the GMM for image segmentation. So like very for the clustering, what is being used for before. And you see, if we do just a normal GMM classification, we got that type of image, and it can be kind of noisy or pixelated if you wish. But within the proportion, you can also use what's called like a Gaussian mixture Markov random field, where you actually include spatial continuity constraint within the definition of the Gaussian mixtures, and that's what you get then in the classification, because it's a lot less pixelated. So there is definitely maybe some application to do on the geological side to force spatial continuities. but maybe, as I showed Nick at some point also, he pointed out that, for example, the eyes that are still visible in the inversion in the GMM here are not visible anymore here. So you have a balance between spatial continuities and small features. So I still have a lot of work to do on that side, but that's where I'm hoping to head next. Yeah, the spatial continuities.
That's very interesting. Yeah, thanks.
So, hi, Thibaut.
Hey, Joe.
I've got a couple questions. So first off, you kind of glossed over it. Hopefully this is an easy question, but why do you need to do MVI? You started saying, oh, we need to do MVI because of this, and then you didn't really quite finish that thought. So
Okay, yeah. Well, I use the MVI, so well, we have the. So like it's true that if we do the single physics inversion, it's not quite necessary because it's all in the same direction. And I agree with that. Like for the single physics PGI with a single unit with only HK, I could have fixed the orientation and say, well, this is the orientation of the field, and you can invert for that. But the real gain is really for when we go to the multiphysics, because here we have two Kimberlite units with different orientation, and I don't know their location prior. So I needed the inversion to be able to have the cells in different direction, but still fall within bins for either the PK induced field or the HK remnant field. Is that?
okay.
If I can answer it quicker, the previous
Yeah.
paper had shown that there was high remnants. So that's
I know why. Just he didn't like complete that thought when he was saying it, so I was asking.
Sure. Yeah. Okay.
Okay. Earlier on, you discussed about how you can weight the update between the prior model, mixture model distribution and the result from the inversion.
Yes.
I guess that you can weight them. I feel like that's a very subtle thing. Can you go into more details about how you weight?
Of course, yeah. So right now I've mostly experimented with kind of like a black and white approach. It's either I like as for most of the case study example where I fixed the physical property values to what I measured in the lab. So basically there is no weighting here. Like so if I take here this example, my prior distribution will be my distribution at all iterations. So that black line will be the same as the gray line. That will be a weight. That will be the weight where I put all the weight on the laboratory prior measurement side. If I put, and I've also, and the other type of experiment is if I put all the weight on the geophysical side. So for example, here that black line will fit the blue histogram here. And that's what I've used in the DC example here. There is no petrophysical information except the number of units. So the algorithm just fits the geophysical model at each iteration, but iteratively you're making them more distinct. And something in between for that approach was what I did for the multiphysics case. So where I have that where I assume that one rock unit is responsible for the magnetic response and one unit for the gravity response. So on those two panels here, I show the mean of the 3 units. So the black is always the background. So the background is fixed. The background is fixed at 0 contrast for both physical properties. So it's all fixed from our priors. Orange here is the HK unit. And so I fixed its density to be a 0 contrast. So this is not moving. But then for the PK unit, I put all the weight of that on the geophysical model. So this one is moving at each iteration. And magnetic susceptibility, it's reversed. The background is still held fixed, but this time this is a pK magnetic susceptibility that is kept fixed at 0, and I leave the HK magnetic susceptibility free. So like all the weight now is on the geophysical model side, and it moves. And then you can think like the things I've experimented less. I've shown some example in the thesis where you put like half weight between, for example, between the two. So that's what I show, for example, in this example here, between the geophysical model in blue and the prior distribution in gray. And I get the black one here. This is basically by putting equal weight for both the geophysical model and the priors. And what I show in the thesis basically is that as you see here, like I didn't like this is a result I get with a 0, with putting like 0 weight for the true physical properties. But if I put additional weights on for a mean outside of the geophysical inversion, it's gonna slowly push it to the true distribution. So there is a continuum here. So like if you have some information but you don't want to if you don't want to force it too much, you might put like a 90 and 10% weight and things like that. But there is I don't have like a good estimate of what to put as weight. And there seems to be a threshold too, like if you put a 50-50 weight between the geophysical model and the petrophysical distribution priors, like a 50% weight is actually enough that it's gonna push the inversions toward reproducing what you put as priors. So
okay. Another question. So you say that this works well when you have good separation between distributions, right?
Mm-hmm. Yes.
Where is the trade-off between good separation and not enough separation?
Yes, so I have a slide for that, and I removed it because it was taking already too long, but that's the slide I have for that. So to explain for you what's the approximation come from is that here I show two Gaussians for representing each rock unit in blue and red, and in the fine black line here is the resulting Gaussian mixtures. And you see like if I have like good separation, like the Gaussian mixtures can be well approximated locally by the dominant Gaussian. So and that's how I get back to a least square formulation, because for example here I will approximate the Gaussian mixtures by the blue Gaussian, and then because it's simply a Gaussian, it translates back to a least square. But then if you have things that are overlapping like that, you see this approximation is not as good. I actually have implemented both within my code. I can handle either the full priors or the approximation. And the main reason why I did the approximations, there are two. There is a practical reason, and that's something I didn't really develop here, but I had the idea at the beginning, was that with that approximation, as I said, I can use compile code and I can use, for example, the UBC code that I can exit at each iteration, rewrite a new reference model and smallness weight, and send it back to the UBC code without modifying it. So there is, for people that relies on legacy codes, it could be something you can build around, and I think that's important. The second one was more like an educational reason, is that imagine that so like you saw that big priors, like with that product with the sum of different of that things, then put an additional minus log in front, and then plug it into an objective function. And it could be very hard at first glance to wrap your head around it, but by making these assumptions, you actually bring it back to a least square formulation that people are much more familiar with, and you can explain it much easier by saying that it appears like updating the reference model and the smallness weight. it was more a choice on me on that it was easier to explain that rather than a very complicated minus log of complex physical property distribution. And I've tested both formulation in my code, so with the approximation and without the approximation. And in most cases that I've worked with so far, like I'm at least at 3 sigmas, so the approximation works quite well, and I haven't seen in those cases any significant difference in the inversion result with or without the approximation.
Okay. So you'll have to forgive me if it's out of place or anything, or I'm not really quite sure how the defenses work at UBC or anything like that, but my recommendation right now,
yeah,
make your answers more concise.
Sure, okay.
Is that unreasonable? Like, does anybody else? Because like, there's a lot of good stuff in your answer, but you're defending your thesis. Like, if somebody asks you a question, you can answer it directly, then do that.
Okay.
Yes, yeah. And then if they ask again, then you can still get longer. But maybe if many people would like to ask, they might get impatient if you spend on each question too much time.
Not even that.
Fair enough,
like
yeah.
if you start like going on long and long, you open yourself up to more and more questions on stuff that you're talking about. So it's always good to answer your questions concisely. If there's a way to answer it concisely, then do that.
Okay. No, that's good advice. Thanks, Joe.
Yeah, otherwise you're giving them a source of just keep asking questions, right? So you don't want to give them.
I mean, it's like you're defending. It's like, okay, it's not like you're a defense. Okay, you're just answering their questions. Like, yes, this is the answer to your question. We understand that you have a very good understanding of all of this. But, I mean, it's kind of like almost like a battle. Like,
yeah.
I probably have a few other questions, but I'll let some other people ask if they have them.
I need to duck out and head to my next meeting, but wonderful job, Thibaut. I'll follow up. I left some notes in the Google Doc, and I do have some questions in mind, but I can follow up with you afterwards on Slack. So I'll hand you the host so that you can continue chatting with folks, and I think that'll keep the recording going. And I can always edit it afterwards if there's stuff that you don't want posted. So just
So who's gonna have the file to upload on YouTube?
I'll still have it. I'll have it.
Okay.
Yeah. All right. Yeah.
Thanks, Lindsay.
Yeah, it was maybe just a quick one. I was wondering, in all your examples,